Welcome back to another explainer. Today, we're opening the case file on Astrophysics' absolute greatest active detective story. It's a mystery that literally forces us to question the very fabric of our universe and the fundamental rules that hold everything together. We're going to be looking at a brand new 2026 scientific report from Half-True Universe Press that asks a really profound question about the cosmos.
Okay, let's dive right into this. I want you to imagine looking at a merry-go-round spinning so incredibly fast that the children on it should be flung right off into the air. But instead, they just sit there, perfectly safely, held in place by some unseen force. Well, that is exactly the paradox we face when we look out at galaxies. They're spinning fast enough to fly apart, yet they stay perfectly intact. Why? Is the universe's most abundant substance just an illusion? Or is there something completely invisible holding the whole shebang together? To make our current mathematical models of the cosmos actually work, we've had to introduce something called dark matter. And here is the truly staggering part. According to the standard cosmological model, this unseen, non-luminous dark matter must outweigh ordinary, visible matter by a massive ratio of 5.4 to 1. So for every 1 pound of stars, planets, and people, there has to be nearly 5.5 pounds of completely invisible mass. Imagine stepping on a scale and realizing 5/6 of your weight is coming from an invisible ghost. That's the sheer scale of the anomaly we're dealing with. It's a massive entity that interacts with our world almost exclusively through gravity.
So our investigation path for today is going to be completely impartial and straightforward. First, a 90-year cosmic anomaly. Second, the case for dark matter. Third, the 40-year particle drought. Fourth, rethinking gravity's rulebook. And finally, the ultimate cosmic showdown.
Part 1, a 90-year cosmic anomaly. You know, this mystery isn't exactly new. It's a cold case that's been haunting astronomers for nearly a century now. Let's briefly trace the timeline. It all starts back in 1933, when Swiss astronomer Fritz Zwicky looked at the Coma cluster and realized the galaxies were moving way too fast. He actually coined the term dunkle materia, dark matter. Then, jump to the 1970s. Vera Rubin and Kent Ford made these ultra-high precision measurements of spiral galaxies and found that the outer edges were spinning just as fast as the intersections. That turned Zwicky's quirky little observation into a full-blown galactic-scale crisis. By 1983, a physicist named Mordechai Milgrom proposed a totally different solution. What if there's no dark matter, but instead our fundamental understanding of gravity is just wrong? He called this MOND, or modified Newtonian dynamics.
The gap between what we expect and what we actually see is just mind-blowing. Based on normal Newtonian expectations, stars farther from the galactic center should orbit much slower, kind of like planets in our own solar system. But the reality, the actual observed rotation curves are completely flat. The stars way out in the galactic outskirts are zooming around at roughly the exact same speed as the stars closer in. This massive gap between expectation and reality is the entire original motivation for the dark matter hypothesis.
Part 2, the case for dark matter. Cold dark matter, or lambda CDM, has historically been the heavy favorite in this mystery, and honestly, for some really good reasons. Dark matter doesn't just solve the spinning galaxy problem, it has these massive macro-scale victories under its belt. For instance, when two galaxy clusters collided in what we call the bullet cluster, gravitational lensing, where light bends around massive objects, showed us that the bulk of the gravitating mass was completely offset from the visible hot gas. That spatial separation flawlessly suggests a collisionless invisible mass. On top of that, precision data from the cosmic microwave background, the relic radiation of the Big Bang, matches the predictions of dark matter perfectly. And when we look at the cosmic web, dark matter provides the exact gravitational scaffolding required for large-scale structure formation to happen early enough in the universe's history.
Part 3, the 40-year particle drought. But here is where we hit our mystery's biggest plot hole. Dark matter has an airtight alibi on the macro scale, but a glaring lack of a physical body. If dark matter is a real particle, like the theoretical weakly interacting massive particle, or WIMP, it should occasionally bump into ordinary matter. So physicists have spent 40 years building multi-ton, highly shielded vats of liquid xenon and argon miles deep underground in abandoned mines. We're talking about massive, ultra-sensitive chambers like Lux Zeppelin and Dark Side. And yet, across 4 decades of these incredibly sensitive underground experiments, researchers have found absolutely zero confirmed WIMP particles.
And guys, this search is about to get significantly harder because we're hitting a massive scientific roadblock. By 2025, detectors actually became so sensitive that they reached what's called the neutrino floor. This is an irreducible background signal caused by neutrinos from the sun scattering in the detectors. It effectively creates a giant wall of background noise, making it progressively harder to distinguish a genuine dark matter signal from just a normal solar neutrino. Why does this matter? Well, because it means we might soon reach a technological dead end where we simply cannot build a better net to catch dark matter.
Part 4. Rethinking Gravity's Rulebook.
All this persistent non-detection leads us to a major plot twist. What if the missing mass isn't missing at all? It completely flips our perspective. Think of it like watching a sports game where the ball keeps changing direction midair. The dark matter approach essentially says, well, there must be invisible players on the field hitting the ball. But the modified gravity, or MOND approach, says, no, there are no invisible players. The fundamental rules of gravity itself change when players move in slow motion at incredibly low accelerations. It's a completely different paradigm, changing the law instead of just adding more mass.
And MOND has an absolutely incredible victory of its own to show for this approach. It's called the radial acceleration relation, which is basically MOND's crown jewel. When you analyze over 150 galaxies of all different types and sizes and plot the observed acceleration against the acceleration predicted from visible matter alone, they all fall on this exceptionally tight, universal curve. For dark matter to explain this, the invisible halo would have to be perfectly, magically fine-tuned to the visible matter in every single galaxy. But for MOND, this tight curve is essentially automatic. It's mathematically baked right into the theory. It's a massive, elegant success.
Part 5. The Ultimate Cosmic Showdown.
So, we have two wildly compelling paradigms. Let's act as an impartial referee for a second and weigh the strengths and flaws of both theories head-to-head. When you map out their qualitative explanatory strength, MOND completely dominates when dealing with individual galaxy rotation curves and the radial acceleration relation. But as we zoom out to the broader cosmos, into the bullet cluster, the cosmic microwave background, and large-scale structure growth, dark matter takes a commanding lead, while MOND really struggles.
Synthesizing this showdown, it really comes down to where each theory shines. MOND elegantly handles galactic rotation curves directly, whereas dark matter has to manually fit a unique halo to every single galaxy. But when we step back and look at big-picture cosmology, like the bullet cluster and those CMB acoustic peaks, dark matter naturally explains them. MOND, on the other hand, struggles deeply. To make MOND work on a cosmic scale, theorists often have to clumsily add residual mass or extra fields back into their equations, which, let's be honest, somewhat defeats the entire purpose of getting rid of invisible mass in the first place.
But wait, because the plot thickens even further with the latest 2026 data. A brand new phase space study using the Gaia satellite just looked at high-precision data from our very own Milky Way. The result? Dark matter fit the Milky Way's radial and vertical data self-consistently. But MOND was statistically disfavored by over 13 standard deviations. Now, in statistics, that doesn't just mean you missed the target. It means you were aiming in the wrong stadium entirely. This shows that as our precision gets sharper, even MOND's home turf of galaxy dynamics is cutting against simple modified gravity models.
So what's the resolution here? Well, the truth is, neither side has delivered a perfect knockout blow yet. The radial acceleration relation discovered by MOND is a very real, very tight regularity that simply cannot be ignored. The correct theory, whatever it eventually turns out to be, is going to have to inherit the genuine, non-trivial successes of both programs. But what we know for absolute certainty is that our fundamental understanding of space-time is being tested more rigorously right now than at any time since Albert Einstein.
Which leaves us with this final, profound thought to take away from today's explainer. Are we spending decades looking for a ghost particle that sits just beyond the reach of our current detectors? Or are we staring directly at a fundamental flaw in Einstein's universe? The dark matter mystery remains one of the genuinely wide-open frontiers of physics, and I really hope this journey has sparked your curiosity to keep following the evidence wherever it leads. Until next time, stay focused and keep learning.